Last week, I introduced you to two of the fundamental forces. Now, I will introduce you to the other two. First is the weak nuclear force. Don't let the name deceive you. The weak nuclear force is much stronger than gravity on small scales. What does the weak force do? It is what allows particle decay to happen, and it can transfer momentum. The weak force acts through the W and Z bosons, particles that are more massive than protons and neutrons. The large mass of the bosons makes them decay quickly, which is why the weak force is weaker than the strong force and electromagnetism, as well as having such a short range. First off, particle decay is transmitted by the W boson. Particle decay is when a quark or lepton turns into another, usually lighter version or flavor of particle. When this happens, the particle either releases a negative W boson to become more positive, or a positive W boson to become more negative. Once the W boson is released, it splits into an electron and anti-electron neutrino if negative, and if positive, a positron and an electron neutrino. Remember, particle decay is ruled by conservation. Conservation of energy, of electric charge, and of quark and lepton number. Have you ever heard that a neutrino can travel straight through the planet without slowing down? This is because neutrinos have no electric charge, no strong force color, or a large amount of mass. The one thing that neutrinos do have is the Z boson. The Z boson just transfers momentum between particles. As a result, neutrinos are sometimes able to slow down. In conclusion, the weak force allows particle decay to occur and gives the neutrino a weak way of interacting with other particles. Finally is the force you are most familiar with, gravity. Gravity is by far the weakest of all forces. Gravity is an oddball among the other fundamental forces. Along with its weakness, gravity has no known carrier particle. The Higgs boson and Higgs field give particles mass, but they are not what makes the mass attract other mass. Protons and electrons are charged by the electric field, but the photon is what makes them attract. As of yet, we haven't found the photon of gravity. Gravity is described by general relativity rather than quantum mechanics. Albert Einstein's theories labeled gravity as the curving of spacetime. There might be a theory uniting gravity with the other forces. String theory, for example, could explain what the Standard Model's particles are made of and incorporate gravity into the mix. Other than the weirdness of what causes it, gravity is very straightforward. Instead of the 6 charges of the strong force, gravity has 1, mass. All mass attracts more mass. The single charge is what lets gravity build up on itself in bigger scales. First, stars. Gravity overcomes electromagnetism and pushes protons together in fusion. In black holes, gravity overcomes the strong force trying to keep the neutrons whole and collapses inward. The gist is this: gravity pulls everything together. Even though its cause may not be fully understood, it just is. Why is gravity different, though? For this, we go back in time to the Big Bang. In the beginning, it was so hot everywhere that all 4 fundamental forces had combined to form one unified force. As things cooled down, the forces started splitting off. Gravity was the first to split. This might be why it is so different from its siblings. Next to split off was the strong force. This left the so-called electroweak force, a combination of the weak and electromagnetic forces. Physicists have been able to combine the theories of electromagnetism and the weak force by studying this force. Finally, electromagnetism and the weak force separated, leaving the 4 fundamental forces we know today. In conclusion, our universe is ruled by 4 forces. These forces pull the strings behind the scenes of the universe. Although there is much to discover, we have come very far as of yet.